Sure. Here's the text with punctuation added. We've all seen the nearby planet group pictures in course books. The Sun, somewhat bigger than Jupiter, yet that isn't the right portrayal of the scales. The Sun is so enormous that you could fit around 1,000 Jupiters inside. Amazing as it is, our Sun isn't the greatest star in the universe or even our system. That title goes to U.I. Scott. Contrasted with it, our star resembles a little stone. But there's something else scientists have coincidentally found. Something significantly more incredible. A mysterious old star with a black hole inside. It's a cosmic mystery that both riddle researchers and can possibly make sense of how the universe came to be what it is today. But how is it workable for a black hole to exist inside a star? For what reason were these stars so tremendous? And what might occur if a black hole star meandered into the solar framework? Stars resemble enormous metalworkers. In their searing centers, they're producing the greater part of the elements we see in the universe. However, the stars that could have existed at the absolute beginning of the universe were something else. Rather than regular heavenly centers, they held onto black holes inside, allowing them to develop to unfathomable sizes and beyond conventional stars. Stars emerge from billows of gas and residue. As gravity makes the densest areas of the cloud break down, the subsequent mass of material warms up and creates a protostar, in the beginning phase in the formation of a star. Ultimately, the newly formed hot core assembles sufficient matter from the surrounding alternating plate of gas, turning into a main sequence star that starts producing energy through nuclear fusion. It took our Sun around 50 million years to arrive at this stage. The majority of stars will burn through half of their life expectancy as main sequence stars. But ultimately, they will all either turn into white dwarfs if their mass isn't enormous enough or go in NOI after a star explodes. Can wind up as a dark hole or, on the other hand, a neutron star. And the way it takes really relies on how gigantic it was. When our Sun runs out of hydrogen in around 5 billion years, it will transform into a red monster, expanding multiple times in size previously. At last, shedding its outer layers and changing into a white dwarf, a heavenly object that is around 200,000 times denser than the Earth, yet about a similar size. The star circle will then, at that point, gradually cool to around 18 million to F10 million to C, and in around 10 billion years the white bantam sun will take shape. The cycles to some degree like how water transforms into ice, albeit the material is different in the instance of the Sun. It will be carbon furthermore, oxygen hardening, and stars more than 10 times the mass of the Sun will have a different destiny. They're large enough for their centers to implode after a cosmic explosion. However, they come up short on mass expected to turn into black holes. So where does this leave them? Somewhere inside these stars, the limit pressure crushes each proton and electron so firmly they converge to form neutrons. Can't be compacted any further, so they counter gravitational strain, and the star finds another fair. Neutron stars are the densest objects known to mankind aside from black holes. They can be simply the size of a little city, about 12 m 20 kilometers. Yet at the same time have a mass of the Sun on Earth. Neutron star material the size of a sugar shape would weigh as much as 1 billion tons, comparably weighty as a mountain. But how do ST stars become black holes while the star is still dynamic? The two winning forces work against one another. Atomic fusion and the extraordinary gravity made by the star's own mass. Attempting to crush it once there's no fuel left to power atomic fusion, there could be, as of now, not a power to counter gravity, and the star breaks down in on itself, very much like the controlled destruction of a substantial structure. Einstein accepted that anything would be able to turn into a black hole on the off chance that it had sufficient mass and was compacted inside a certain span. Black holes continue to develop all through their life expectancy, gobbling up any material that gets excessively close. When this happens, the wear gravitational force turns out to be such an extent that nothing would be able to escape. Increments, and the dark opening consumes much more close by material. It's rather like the sinking of ground due to the breakdown of underground structures, in spite of the fact that with dark openings it is a gravitational sinkhole continuously evolving rapidly as its occasion skyline develops. Ordinarily, dark holes have a breaking point on how quick they can grow. This occurs because of something many refer to as the Eddington radiance limit. Fundamentally, it's the point at which a dark hole can't take in material quicker than it as of now does. On the off chance that you were filling a vehicle tire with air also, It had little openings in it. The expanded tension inside would make a portion of the overabundance air get away in space. Something very similar occurs with turning dark holes. As issue twistings toward a dark hole, it goes increasingly fast. Due to this, around 42% of this can be changed over into energy, and this radiation is so strong it can push a portion of that approaching material away. Like a vehicle tire drives the air away, this process is so effective the radiation radiated away outperforms the energy yield from atomic combination and stars. Just envision a future where we track down an approach to harness this energy and use it for our needs. Considerably more enormous dark holes with a huge surface region that draws in matter have this breaking point. They are at the focal point of pretty much every cosmic system out there. Also, a portion of these very enormous dark openings have been as of late found to be a lot bigger than we felt. That is one of the best secrets in space science. The progressive amassing of matter over the age of the universe neglects to make sense of their huge size. However, there's something that could disentangle the secret dark opening. Stars or semi-stars probably been the largest heavenly bodies to at any point exist, overshadowing even the most monstrous dark openings we've found. Set up to this point today, the states of the universe don't permit dark opening stars to frame. However, at the dawn of history, space was loaded with monstrous gas mists. Inside these thick locales of room, material imploded in on itself under its own gravity. And since there was a lot more of it stacked up, leading to child stars of exceptional extent, in spite of the fact that there's a thought that they might have started from dull matter, radiance is undetectable round areas of dim matter up to 100 million solar masses where huge number of very monstrous stars could structure. Typically, enormous stars would go cosmic explosion and abandon huge dark openings. Yet these divine Goliaths weren't simply enormous. They were so gigantic their size permitted them to retain the hazardous force that would somehow or another shoot the star's outer layers out into space. Rather, these old stars, as it were, experienced collapses, which changed their heavenly centers into minuscule dark openings while keeping the external layers flawless. If you would somehow or another see this peculiarity from a close distance, you wouldn't see any progressions with the star. Now that there's a child dark opening inside a semi-star, it begins eating it from within. As of now, the dark opening is minuscule, yet it's turning, and this makes a plate of hot material surrounding it at almost the speed of light. On top of that, there could be, as of now, not a breaking point on how quick it can gobble up gas as the star's pressure sends it straight into the dark opening. The grating inside the gradual addition circle turns out to be increasingly hot, producing lots of radiation and making the host star gleam like a little system. Semi-stars, assuming they existed, became quicker than any dark opening we've at any point noticed. In the long run, inside great many years, some of them would beat the largest stars and dark openings in size that we know about, like Stephenson 2 to 18 UI and T618. Just how enormous is that? From large numbers of times s bigger than the Sun to possibly even the width of our planetary group and past. Yet this huge size and mass additionally causes issues the larger semi-stars become. The more limited their life expectancy. Our Sun has been around for more than 4 billion years, with around 6 billion years left in its life expectancy, while dark opening stars gone on for only a couple million years before fantastically detonating with uncommon power, delivering an ever-hungry colossal dark opening prepared to float across space looking for more material to eat up. But imagine a scenario in which a star like this meandered into our tranquil divine area. Once a semi-star found its direction into the planetary group, its gravitational impact would disturb the laid-out circles of planets and heavenly bodies. The once methodical planetary framework would be in complete disorder, with Earth encountering an extreme space rock downpour. The effects would start before the semi-star entered our solar framework completely, as the huge star swallows the outer planets and other heavenly bodies. Our planet would, as of now, experience a flood in temperature and luminosity, making the surface aloof until at last, it would consume the Earth as well. Although life here would long be gone by then, the focal dark opening H inside semi-stars might have filled in as seeds for the development of very huge dark openings that are at the focuses of worlds today. And they could have even played a bigger job. The powerful cycles related with semi-stars, for example, the breakdown of the focal dark opening in collaboration with the encompassing matter, could be strong wellsprings of gravitational waves, which, in turn, may have played a job in the arrangement of cosmic structures and the dispersion of stars inside G-worlds. But, in addition to that, semi-stars could have suggestions for astrobiology. The extreme radiation from these items could have impacted the tenability of planets in their area, possibly shaping the conditions for life unexpectedly. That said, with regards to infinite development, Semi-stars could have set the future by molding the early universe in incomprehensible ways. But here's another.